My name is Mariano Zeron, and in this video I'm going to show you how we can come up with an algebra of Chebyshev objects. So the situation is as follows. Let's assume that we've got two functions to begin with, f1 and f2. And for each and one of them, we've already built a Chebyshev object. Let's call it p1 and p2. Now, what we're interested in are combinations such as this. So it's basically the multiplication by a scalar of f1 plus the multiplication of a scalar that we call here lambda2 times f2 in order to come up with a new function f. So this is sort of in an abstract way, but think of it in terms of a portfolio where you have possibly thousands of trades. It would be, for example, trade 1 would be f1, trade 2 would be f2, lambda 1 and lambda 2 could be adjustments to the notional of the trade. And what we're interested in is, instead of building a new Chebyshev object for the function f, which represents in some respects the pricing function for the portfolio, you want to be able to use the already existing Chebyshev objects, p1 and p2, define appropriate multiplication by scalars and addition so that we can come up with a new object, p, that hopefully will be a good approximator to f. And if we manage to do that, then not only will we be able to construct an approximator to the whole portfolio very, very quickly, but also we can start carrying out what-if analysis, such as, let's assume that the portfolio that it starts off with just consists of this function over here. If you want to add a new trade and come up with an approximator to the pricing function for that new portfolio, you could do it by simply taking the existing Chebyshev object and adding a new Chebyshev object, the one that corresponds to that. You could also take away a trade from a portfolio, and you would do it in a similar way, basically. You want to take away from the existing portfolio, which is this one. You want to take away that trade, just simply take away that Chebyshev object from the existing portfolio, from the Chebyshev object representing the existing portfolio, and you quickly get the new object that approximates the resulting portfolio. So basically, we've got two operations to define here. One of them is going to be multiplication by scalar, which we will define at the end. Is very straightforward. And the other one is addition, which is a bit more complicated. But let's focus on that one for the time being. So we have f equals f1 plus f2. That's going to be the focus, at least for this part of the video. And essentially, what we want to define is p1 plus p2. That will give us some p that we still have to see how to obtain. And then at the end, I'll justify how this p is a good approximator to f. So, of course, one thing that you could have already thought of is, I've got f, I can build a Chebyshev object directly for it. The problem is what happens if you don't have only two functions here, but you've got 1,000, which could very well be the case in a portfolio that consists primarily of a single trade type, all the trades relying on the same risk factors. Of course, building a new Chebyshev object for that portfolio is going to be a bit expensive. Okay, so let's go into defining p1 plus p2. So first case that I'm going to use to illustrate what the spirit of the definition is. Take f1 and f2 such that they share the domain. So it's the same domain, not only the same domain, but the same number of Chebyshev points. So the Chebyshev objects have the same size. That would be the case, for example, that we've got over here. So P1, this Chebyshev object, has n plus 1 terms. That is, it was defined on n plus 1 Chebyshev points. P2, the same case. So how do we define P in this particular situation, where it's going to be P1 plus P2? That is going to be given by this sum, where the coefficients are just going to be the addition of the corresponding coefficients, which, of course, can be expressed in terms of Chebyshev polynomials or Lagrange polynomials. So, pretty straightforward. However, this is a very, very particular type. I'm assuming that the domain of approximation coincides and that you've got the same Chebyshev points. What happens if that is not the case? So the first thing that we have to first of all assume is that the two objects that you're trying to add share some part of the domain. That is, the domains overlap. Because if the domains did not intersect at all, you wouldn't be able to define the addition of the objects. So basically, we're assuming that we've got at least this kind of situation. So for P1, you've got this domain. For P2, you've got this domain over here. I'm going to denote the Chebyshev points for P1. So P1 basically has this domain over here. Chebyshev points here. And for P2, we've got Chebyshev points here, which notice they won't necessarily, well, that's not necessarily that one, they won't necessarily coincide with the Chebyshev points of the other objects, not even in the bit of domain that they share. So what can we do with that? So this is P2. Also, another assumption that I'm making is that the Chebyshev objects have the same dimensionality. What would happen if they don't have the same dimensionality? You may remember from one of the videos that we have that there are two operations that you can carry out on Chebyshev objects in our library. So in our library, they're called MOCX objects. There's two operations that we've incorporated into the library, which are extrusion and slicing. Extrusion is a way of extending the dimensionality of an object. Slicing is a way of reducing the dimensionality of the object. So if you started with P1 and P2, two Chebyshev objects that don't have the same dimensionality, but you want to add them, you can adjust the dimensionality of one of them so that they have the same dimensionality. And if the domains coincide, then you can carry out the addition. So at least for this part for this part of the video, or at least throughout the video, we assume that both Chebyshev objects have the same dimensionality. So what are the main ingredients that we need in order to build a Chebyshev object? We know it's specification of domain, specification of the number of Chebyshev points on that domain, and then values on those Chebyshev points. So the first one here, domain. Domain is obtained by the intersection of the corresponding domains of P1 and P2. In this case, it's this over here. Second, number of Chebyshev points on that interval. And we define the number of Chebyshev points, which is going to be k, as the maximum of n and m, where n and m are the Chebyshev points for P1 and P2 respectively. So here I've modified P1 and P2 so that they have the corresponding Chebyshev points that I'm assuming here. And let me just write down, for reference, we've got n Chev points, and for the other one, we've got m Chev points. And we take the maximum of both of them. So k is going to be the maximum of both of them. That specifies the Chebyshev points on this interval, which again, they don't need to coincide with any of the Chebyshev points from the objects P1 and P2. Perfect. And the third part that we need are the values on those Chebyshev points. And these are going to be denoted by Zi. And Zi is going to be defined by P1, what do you call it, is Pn supraindex 1 at xi plus Pn. I'm going to take away the 1 because we know that Pn is the first Chebyshev object and Pm is the second Chebyshev object. So Pm on xi. That's the definition. And with this information, we can come up with an object. Then we can evaluate using the barycentric interpolation formula. So essentially, the object that we have, and I'll write it down in a second, I'm just going to expand what Pn of xi and Pm of xi is. Because remember that Pn is an approximator to F1. So this is basically here Pn, this is Pm. this is an approximator to f1, and this is an approximator to f2. So this is going to be the same as f1 at xi plus some error that I'm going to denote by epsilon 1 I plus f2 at xi plus epsilon I2. Of course, this is going to be equal to f, because f is just f1 plus f2 at xi plus the corresponding errors. And now I can write the expression that we're interested in. pk, is going to be given to you by this sum over here. So that's going to be our candidate. And this is the way that we build this object here, P, which is going to be the approximator to F. So as you can see, it uses Pn and Pm, basically the Chebyshev objects that we started off with. So the evaluation of these objects we know is completely straightforward, is stable from a numerical point of view, is very efficient. So coming up with these ZIs is completely straightforward. Hence, this expression can be obtained in almost no time, which of course is a stark contrast to if you had built a Chebyshev object directly for F. So of course, it makes much more sense to build it this way, at least in terms of efficiency. Now, let's see how it is in terms of accuracy. So what we're going to be interested in is seeing what happens with this expression. P pk at x, where x is just a generic point in the domain, minus f of x. This is the expression that we're interested in seeing how it behaves as k tends to infinity. So if we rewrite that in terms of the definition of pk of x, what we have is this. And if we use what zi is, this is equal to f of xi plus epsilon I1 plus epsilon I2 times Li of x minus f of x. All good so far. We take Li of x inside this sum, which means we've got f of xi times Li of x plus another sum where we have the errors. And then here we've got f of x, and then a crucial inequality where basically we're going to put this and that term together, and that's going to be very important, as we'll see in a second. So we've got this plus perfect. So what do we have so far? Here, you can notice that what we've recovered is the expression of the Chebyshev object that corresponds to f, as if we had built it, essentially. But we know that this expression here tends to 0 exponentially and uniformly as k tends to infinity. That already comes from the properties of Chebyshev objects. Perfect. Now, what we have to take care of is the expression on the right-hand side. Now, here we've got a collection of errors that are specific to the Chebyshev points. But we know, for example, and I'm gonna write it over here, that we know that the epsilon I1, that is less than or equal to epsilon 1, where that is basically the error that Pn makes as an approximator to F1 with the supremum norm. Also, we know that this is less than or equal to epsilon 2, that we define as the error that Pm makes with respect to F2 as an approximator. So hence, if we define epsilon as epsilon1 plus epsilon2, we're going to mark this, this definition over here. What we know is that then this term over here is essentially, well, this is going to be less than or equal to the same thing here, plus, I'm just going to take it out already, this is going to be less than or equal to epsilon times the sum of the absolute values of Li of x, right? One good thing is that this epsilon over here is defined in terms of epsilon1 and epsilon2. But these epsilon1 and epsilon2, we know that these things tend to zero exponentially. Again, because Pn and Pm are Chebyshev objects. And we know that one of the properties of Chebyshev objects, if we're dealing with functions which are analytic, which we're assuming all the way through, is that they converge exponentially as n tends to infinity in this case, and as m tends to infinity in that case. Beautiful. So what we know is that this will tend to 0 as n and m tend to infinity. We also know that this term tends to 0 exponentially as k tends to infinity. So the only term that remains to be addressed is this one over here. And that one is a very particular expression. This expression, we're going to call it lambda x, is, let's call it lambda k of x, is called the Lebesgue function. The Lebesgue function for these set of points over here, for the Chebyshev points that we've defined here. So the Lebesgue function is a function expressed in terms of Lagrange polynomials. Lagrange polynomials themselves depend on a collection of points that you've chosen. And regardless of the collection of points that you've chosen, this Lebesgue function has a particular property. It has the property that the supremum of lambda k of x tends to infinity as k tends to infinity. That is the case always, regardless of the collection of points that you choose. However, when you choose Chebyshev points, and this is again another amazing virtue of Chebyshev points, the divergence takes place as slow as you could expect it. And the divergence is logarithmic. So essentially what you end up with is the possibility of, first of all, bounding this above by the supremum of the Lebesgue function, which is this. That is going to diverge logarithmically. However, as n and m tend to infinity, this epsilon converges exponentially, hence completely dominating the logarithmic divergence and having as a result that this expression over here that we were interested to begin with gets smaller and smaller exponentially as n and m tend to infinity, and that it's independent, that's very important, it's independent of the x that we choose here, simply because all the arguments that we've made so far, which is that the epsilon tends to 0, independent of the x, as we can see from here, this also, the Lebesgue, the supremum of the Lebesgue function automatically doesn't depend on the x, and also this tends to 0 exponentially, independent of the x, simply because it's, again, a Chebyshev object. So as a result, what we have is that the pk of x, which is the candidate that we defined to approximate the function f, is a good candidate to approximate it. And as we saw in the first part of the video, obtaining pk of x is completely straightforward. So we've got a really good combination of having a way of coming up with a new object, a new approximating object from already existing ones that has essentially the same properties that Chebyshev objects have, which is that they're phenomenal. They've got phenomenal accuracy, and that they can be evaluated using the barycentric interpolation formula. And with this, what we've defined is the possibility of adding 2 and hence more Chebyshev objects to completely finalize the definition of this thing that we call the algebra of Chebyshev objects, The only thing that remains is the definition of a multiplication by scalars. And as you may already have guessed, that is completely straightforward. You start with one Chebyshev object. That can be, for example, I'm going to rub out the domain of the two Chebyshev objects that I had just below. In fact, I'm going to delete this as well here. If I start with, let's say, Pn of x, which is this expression, or alternatively, this expression, clearly lambda times Pn of x can easily be defined by lambda ci ti of x, or by the sum of lambdas times vi li of x. The thing to remember really here is that the Chebyshev object as such is given to you by these coefficients, either the vi's or the ci's. And when you have the ci's, you know that there are algorithms that allow you to evaluate it really easily using just the ci's and the x that you want to evaluate the x in question. Or alternatively, if you've got the vi's, you can use the barycentric interpolation formula, but it only depends on the vi's. You multiply by a scalar, you're essentially just multiplying the coefficients of vi's by this scalar, and then the rest is as it was before. So there's nothing really that you need to do. And of course, all the approximation properties clearly, trivially follow through without any problem. So once we've defined this algebra operation, what you can do is add and multiply trades, any number of trades that you have, and you can start doing all sorts of exercises of adding new trade, defining a new object that approximates the pricing function of the whole portfolio, carrying out some risk calculation, see whether the metric is a good one. You like it, incorporate the trade. You don't like it, remove it. Do you want to get rid of a couple of trades in order to improve certain metric? Get rid of them. You'll be able to update the Chebyshev object of the whole portfolio really quickly using this definition. Compute the metric, and off you go. In a very simple way. So this is all there is to say about the algebra of Chebyshev objects. Hopefully you've got some questions so that you get in contact with us, because we love hearing from you. And see you next time. Thank you very much.